Design of bath towers for gas absorption. Compared to the design of plate absorption towers, which is concerned with the total number of trays to be used, the design of bath towers is concerned with the derivation of the tower height equation. Alongside with this derivation, operating line derivation, determination of optimum liquid to gas flow ratio, and the measurement of the film and overall mass transfer and coefficients are also important in the design of bath towers for absorption. Since this lecture intends to tackle only the molecular level of gas absorption, we'll discuss only down to the measurement of the film and overall mass transfer coefficients. First, let's look at the operating line derivation. Here is a simple illustration of bath absorption tower. Bath towers are designed in a manner that the streams flow counter-current or opposite direction with one another. The gas, which total flow is represented by V, flows upstream, while the liquid, which total flow is represented by L in the illustration, flows down. Based on this illustration, the overall material balance of component A or the solute will be as shown in this slide. In the material balance derived, it is assumed that no liquid vaporizes during the process and that the only component of the streams are the inert and the solute A. At first look, it is hard to understand why the material balance look like this way, but by performing dimensional analysis on each term of this equation, its validity will be proven. Consider the first term L prime times the quantity x sub 2 over 1 minus x sub 2, where L prime is in kilomole inert liquid per second, x sub 2 is in kilomole A per kilomole inert gas plus kilomole A, and 1 minus x sub 2 is the mole fraction of the inert gas, which is in kilomole inert gas per kilomole inert gas plus kilomole A. After cancelling, the unit of the whole term will be kilomole A per second. That is the number of moles of A present in the liquid stream upon entering the tower. The same dimensional analysis applies to the other terms. So getting the material balance around the dashed line will give us the equation of the operating line. X sub 2 and Y sub 2 are replaced with X and Y respectively. X and Y represent the mole fraction of A at any point in the tower. From this equation, we can now construct the operating line. Since L prime and V prime are constants, when pairs of X and Y are plotted in the XY plane, the operating line will be constructed. For gas absorption, the operating line is above the equilibrium line. Gas absorption is a transfer of soluble A from the gas stream to the liquid adsorbent. There is also a case where the operating line is below the equilibrium line. That is for the case of stripping, the opposite of gas absorption. In stripping, the solute A transfers from the liquid to the gas stream. Though it is not obvious in the illustration shown, when this operating line equation is plotted, a curve will result. The operating line can also assume a straight line when x and y are very dilute. The denominators will be equal to 1 for this case since x and y values are negligible compared to 1. Another form of the operating line equation will be in terms of partial pressure. Y sub 1 over 1 minus y sub 1 will be replaced with PA1 over PT minus PA1. Well, that's all for the operating line derivation. Let us now move on to the optimum L prime over V prime ratio determination. Why do we need to know the optimum L prime over V prime ratio? This optimum ratio is useful in preventing flooding. Flooding occurs when the velocity of the gas stream which flows down upward hinders the downflow of the liquid stream. It is also useful in minimizing cost of the tower. Choosing a very high L prime over V prime ratio will require a tower with a large diameter. Here, the recovery of the solute will be costly. On the other hand, choosing a very low L prime over V prime ratio will require a very high tower. For this case, the construction of the tower will also be costly. So where will L prime over V prime ratio depend? For a packed tower, V sub 1, Y sub 1, Y sub 2, and X sub 2 are usually set. So only L prime can be adjusted so as to optimize the L prime over V prime ratio. A higher L prime will result to a higher L prime over V prime ratio and vice versa. When is L prime minimum? When the operating line intersects the equilibrium line, L prime is minimum. At this point, the mole fraction of A in the liquid is at maximum and no driving forces are present. Therefore, no mass transfer is taking place. If the equilibrium line is curved concavely downward, L prime is minimum at the point where the operating line becomes tangent to the equilibrium line. The determination of the tower value and the L prime over V prime depends on the value of solute and the tower type. We must choose the L prime over V prime ratio, which minimizes the cost of the tower construction and operation while maximizing the efficiency of the packed tower. That's all for the optimum L prime over V prime ratio determination.